In this lecture, we will continue our discussion on assembly languages.
So here we can describe how we use assembly language to translate algorithms into programs that can be executed on a von Neumann computer. Now, today, programmers are using high-level languages rather than assembly language. I mean, there are some exceptions to that for very special purpose tasks, but the whole purpose in discussing this is we want to demonstrate how system software, and in this case the assembler, can create a user-oriented virtual environment that supports effective and productive problem solving. Now, one of the most common operations that we can do in an algorithm is the evaluation of arithmetic expressions. So what we're going to do here is just look at some examples of how we do these arithmetic expressions in the assembly language. So here is some assembly code for setting the value I to 1. And notice first of all how readable this code is compared to the machine language. Because with machine language we had to use a bunch of ones and zeros. But here we can at least have an idea of what's going on. And we can use opcodes such as load and store, and then the pseudo ops such as the .data. So notice that down here at the bottom, so I'll circle this for you, is that we have the code for setting our variables. So we're setting I to 0 and 1 to the number 1. So up top, we load 1, so we put 1 into register R, and then we store that value into I. So store I means that we're going to store the value in the register into I, and then maybe we'll do some stuff later on, and then we have this instruction right here called increment I. If I could draw an arrow, that would be good. Close enough. But here, this increment I operation means that we're going to add 1 to memory location I. So, I mean, this is a lot easier to interpret than with machine language. Here is another example of an expression where we're trying to compute A equals B plus C minus 7. Now here we're going to assume that B and C already have been assigned values. Here it looks like it's 0, but let's just assume that there were some loads earlier that assign some values. So here we would have up at the top, and we're going to load B into the register, and then we're going to add C to the register. So that means R now holds B plus C, and then we do the subtract 7 instruction, which now means that we're going to subtract 7 from the value of the register, and then we just store that in A. So once again, this is just, it's very simple to understand that we are doing all these computations. Another important algorithmic operation involves testing and comparing values. The comparison of values and the subsequent use of the outcome to decide what to do next are termed a conditional operation. So let's take a look at an example of this where we have a conditional that outputs the larger of two values x and y. So here's how we can express it as an algorithm. So we would input the value of x and the value of y. If x is greater than or equal to y, then we'll output x, otherwise we'll output y. Now let's take a look at how this conditional operation can be translated in assembly language. So we see at the bottom that we have data stored for x and y, initially 0, and then we go all the way up to the top and we basically follow the same algorithm. So in this instruction just simply means input. So we're going to input x and we're going to input y. And then we're going to do a load y instruction, which means we're going to load y into register R. And then we're going to do our compare operations and compare x to the value in our register. And then as we talked about before, this will set the condition codes, the GT, the EQ, and the LT codes. So then we're going to do a jump LT parity. So if x is less than y, then we're going to go to the parity label. So we're going to jump all the way over to here if this is true. Now, if it's not true, then that means x is greater than or equal to y, which means we'll skip that instruction and go to the next line, which is to out x, which means we're going to print the value of x. And then the next instruction would be to say jump done. So we will skip the next line and jump all the way to the instruction labeled done. So that's right here. Now, if we jump to the parity label, then that means we're going to out y, which means we're going to output the value of y because that means that y is in fact greater than x. Another important algorithmic primitive is looping, and we talked a little bit about looping before. So let's just look at a simple example where we would execute a loop 1,000 times. So we're going to say set I to 0, and while I is less than 10,000, we'll do something. We're not too worried about what that something is right now. But the last step of the body of the loop is we're going to add 1 to I. We're incrementing I by 1. So we're going to go back into the while loop, and we'll keep repeating this 10,000 times. Once we're done, we'll get out of the loop, and then we'll stop. We can easily translate this into assembly language. So let's take a couple minutes and look this over. So at the bottom, we have 3 different values that we're storing. We have a 0, which is going to initially be 0, I, which is also going to be 0, that's going to be our loop counter, and then this max val. This is going to store the 10,000 for us and tells us the maximum number of times we're going to execute our loop. So now let's go to the very top. So load 0 means that we're going to initialize the loop counter to 0. So we're going to store the value 0 into our register, and then store I means we're going to take that value that's in the register and store it into I. So that's how we store I into 0. Yes, I know we initialized the 0, but let's just go with it anyway. And then we're going to load the max val. So we're going to put 10,000 into register R, and then we're going to compare that value with I. And so we're going to check to see if whenever I becomes 10,000, we're done with our loop. So that's where this jump EQ done instruction comes into play. So if this is actually true, then that means I is at 10,000, we're done, we can jump to done, and we're saying we're over with. But if it's not true, we're going to move on to the next instruction, and it's going to be whatever we want to do inside the body of the loop. We have our increment I instruction, so we're going to add 1 to I, and then jump loop is going to have us come back to the instruction labeled at loop, and we just keep repeating this until I becomes 10,000. And then at that point, we'll jump over to done, and then we see that we have a halt, so we would stop executing. We'll look at one more example, and we'll actually show a complete assembly language program, which includes all of the necessary pseudo-ops. So we're going to solve the following problem. We'll read in a sequence of non-negative numbers, one number at a time, and we'll compute a running sum. When we encounter a negative number, we'll print out the sum of the non-negative values and then stop. So the way we're going to do this is pretty simple. So we're going to set the value of sum to 0. We'll input the first number, which we'll denote as n. And while n is not negative, we'll add that value of n to the sum, and then we'll input the next dative value for n. And we'll just keep repeating this until n is negative. Once that happens, we'll print out sum, and then we'll stop. So now let's take a look at how we do this in our assembly language program. So at the bottom here, we see that we have 3 values that we're storing. So we have a 0, which is going to be the constant 0. We have our n, which is going to store our input data. And then our sum, which is going to store the running sum. So at the very top, we have the dot begin to let us know that we're at the beginning of our assembly language program. And then we'll clear sum. So this is going to just reinitialize sum to 0. In n, we'll input our first number, and then we'll load 0 and put that into our register. We're going to do a comparison with n and 0 to determine whether n is a negative number or not. So we'll compare n, and then we're going to do a jump LT instruction if n is less than 0, because if n is less than 0, then that means it is a negative value. So we're going to jump to neg, which means that we're going to output the value of sum and then halt. Now, let's say that's not the case. So let's do the rest of this. So the load sum means we're going to store sum in our register, and then we're going to add n to it, and then we're going to take that value and store it back into our sum. So we're always using the register for updating our values. So once we have updated the value of sum, we'll input n again, and so we'll do an in n instruction to get the next input value. And then we're going to do a jump again instruction, which means we're going to jump back to the again instruction, so the instruction that's labeled as again, and then we're just going to compare again and just keep doing this until we encounter a negative number.